This is the last probability topic that's discussed in section 5.6 of your text, and it's permutations and combinations. This is a topic you may remember from middle school or your freshman year of high school if it's not something you totally blocked out of your memory because it was a traumatic experience. A permutation, the notation that the book uses for this is P with NK next to it like this. Other notation you may see is NPK written like this. What a permutation does is it counts the number of ways n distinct objects can be arranged, k of them at a time, where the order of the objects is important. This is the formula that we have for a permutation. This is n factorial, it's not just an excited n with an exclamation point, divided by n minus k factorial. What a factorial is it just means we multiply by every number less than that number until we get down to 1. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. And 4 factorial would be 4 times 3 times 2 times 1, which ends up being 24. Some key terms to look for in word problems that want you to use a permutation are arrange, order, line up, questions that deal with sports sometimes, permute. Also situations where there are distinct roles or jobs that need to be filled. But pretty much any type of situation where you care about the order or you want people or objects placed in distinct positions. And now let's have a math joke about factorials that I would still find a way to sneak in if we weren't quarantined. So let's say we want to add an exclamation point to the following sentence. I want $50 in my bank account. Now, if you're not somebody who knows what factorial means, you might be tempted to put the exclamation point over here. If you know what factorial means, and now you do, you're going to know you want to put the exclamation point here, because that number is a lot bigger than 50. The other thing in this section that we're going to be talking about is combinations. Combinations have a little bit more notation. So they have similar notation to the permutations. Like here we have CNK and CK like this, which pretty much parallel the notation that we have for permutations. Then there's this additional one here where it looks like we have parentheses and the n on top of the k. This would actually be read as n choose k. And what a combination does is it counts the number of ways n different objects can be put into groups of size k. The order of the objects in the groups doesn't matter. The formula we have for a combination here is n factorial divided by n minus k factorial times k factorial. Key terms you would look for in word problems are things like choose, select, group, problems about committees, also sometimes problems about food unless they give you something else to indicate that order is important in the question. So you can use these two formulas, but you don't actually need to memorize either of them. I'm going to show you, after we get through an example, how you can calculate combinations and permutations on your calculator directly. But you do need to be able to recognize if a problem requires you to use a combination or a permutation in order to solve it. Now we'll take a look at this example. So suppose we have a collection of 5 films. We want to see how many ways we can arrange 3 of the films on a shelf. And then we want to see how many ways we can choose a group of 3 movies to lend to a friend. Before we start solving, we're going to need to determine, are we going to solve this with a combination or a permutation? If we want to arrange 3 of them on a shelf, the word arrange here lets us know order matters. In part B, we want to choose a group of 3 to lend to a friend. So it doesn't matter what order you present the movies in, you just care about what 3 movies you're lending to someone. So this is a situation where order is not important. So we can use a combination here, and in this one, we'll use a permutation. Now in this problem, let's call the movies, we'll call the films A, B, C, D, and E. There's 5 of them. We'll look at a way that we can solve this without using the formulas, and then we'll see how we can solve it with the formulas. Part A was asking how many ways can we arrange 3 of them on a shelf. That means we care about the order. So let's say, A, B, and C is one possible arrangement. Well, then we could also look at BAC, we could look at CAB, ACB, and that's every way that we could possibly arrange the films A, B, and C if those are the only ones we picked. Now we can also go through this for the other movies. Now let's say we are going to, exclude C. So we could have A, B, D. We could have A, B, E. We keep looking at this. Okay, this is going to be a lot of things that we would have to list out. We could solve this by hand like this by writing out all possibilities, but, again, this is going to be a lot of work, right? So we have, for each of these different groups, we have a whole bunch of different ways that we can arrange them. So if we were to use our permutation formula, right, we have 5 movies, and we want to permute 3 of them. So that's going to be 5 permutation 3. We plug it into the formula that we have. So we end up solving this, and we end up getting 60. So that means if we were to have written all this out by hand, we would end up having 60 different things here, which is, that's a lot of work. Nobody wants to do that. I don't know, maybe somebody wants to do that. I'm not judging you. We could have 60 things. Now, if you notice, if we get down to this part here, after we've simplified everything, we have 5 times 4 times 3. We also could have solved this using the product principle. So if you remember from a couple videos back when we talked about the product principle, this is a problem that we could also solve with that idea. We could say, well, we have 3 positions on the shelf, and now we want to consider how many movie choices we have for each position on the shelf. Now, we can't repeat the movies that we put on the shelf because we're going to assume we only have one of each movie. We don't have some type of cloning machine that'll let us make duplicate copies of a movie, right? So there's 5 movies that we can choose for the first position on the shelf. There's 4 that we can choose for the second position on the shelf since we've already placed one. And then there's 3 that we can choose for the third position on the shelf because we've placed 2 other ones. And if we multiply all of this out, we get 60. Now let's say that you want to solve this on the calculator and you just want to know what to recognize. Okay, first you would want to hit the math button. It's going to take you to this screen. Now, the first thing that you're going to see, it's going to take you to this screen. Then you're going to want to use this arrow to go over to the probability, highlight PRB up here. Now you see 2 things, NPR and NCR. NPR is what you would use to find permutations. NCR is what you would use for combinations. You also might notice the exclamation point down here. This you can use to calculate factorials. Now we wanted to do a, what was it? Oh, no, messed this up. Right, so we want to calculate 5 permutation 3. If you have one of these, you need to put in 5 first if you have a TI-83. If you have a TI-84 or higher, it's going to be more user-friendly. You just won't need to put in the number 5 first. So we hit 5, we hit math, we go over to probability, we hit NPR for permutation. We want to do the permutation of 5 permutation 3, so now we put in 3. Then we hit enter and we end up getting 60. Let's go back to part B of this problem. We want to see how many ways we can choose a group of 3 movies to lend to a friend. So here we don't care about the order. If we just care about the group of movies that we're choosing, we can look at the work that we did over here. And so if we were to write these out, in a permutation, all of these are different, distinct groupings because we care about the order of them. If we were looking at a combination, all of these things are repetitions of each other. Right? We don't care what order they're in, we just care who's in what's group. So you're going to always have less answers for a combination than you are for a permutation. And if we wanted to try and write out all possible groupings by hand, that might be something that we could actually do. But we have a formula, so we can solve it that way. So we want to do 5 choose 3. So according to the formula we have over here, it's going to be 5 factorial. Oh, and just something to clarify, n is always the larger one. Sometimes people will confuse n and k. N is always the larger number, k is always the smaller number. This is going to be 5 factorial over 5 minus 3 factorial times, oh, no, factorial's on the outside. It's going to be 5 factorial over 5 minus 3 factorial times 3 factorial. And we can start to simplify this. This is going to be 5. Right, we can expand out 5 factorial, then this becomes 2 factorial, and we can expand out the 3 factorial over here, and some of these guys cancel already. Now we end up with 5 times 4 over 2 times 1. That cancels, so we just end up with 10. We can't use the counting principle to solve combination problems because if we want to use counting principle, that has to be a situation where order is important. So just to summarize, we can use permutation when order matters and repetition is not allowed. We can use the counting principle when order matters. We can use the counting principle when order matters, repetition is or is not allowed. And lastly, a combination, order does not matter. In a combination, order doesn't matter and repetition is not allowed. The only situation where repetition is allowed is counting principle and order has to matter. Permutation, order matters, repetition is not allowed. Combination, order does not matter, repetition is not allowed. There is some overlap between permutation and counting principle, but there's not overlap between combination and the other ones. So let's look at some more examples. Let's look at another example. So there's 402 recruitable villagers in Animal Crossing New Horizons. How many different ways can a group of 10 villagers move to your island? What if we care about the order that they move to your island in? If they're first asking us just how many different ways can a group of 10 come to the island out of the 402, that would be a combination because we don't care about the order, we just care who's in the group of 10. The next thing we're asked is what if we care about the order that they move to the island in? This means we care who comes first, who comes second, who comes third, and so on. So that would be a situation where order does matter. If we just care about who's in the group of 10, the answer to that would be 402, choose 10, which is a very large number I'm not going to bother to write out. And the other situation is if we do care about the order that they move in, this would be 402, permutation 10, which again is another ridiculously large number. But this just illustrates the difference between when we would use a combination and when we would use a permutation. And yes, if you play Animal Crossing and you see these ridiculously large numbers, this is how many different possible ways you could end up with a grouping of 10 villagers. Let's look at one more problem. So this is one problem where you're going to have to distinguish between whether you can use a permutation, the product principle, or a combination in order to solve it. So if you want to pause the video here and try and solve it yourself, you should do that now, and then I'll go through the solution with you. Here we're told a bakery has 9 different flavors of cupcakes and would like to display 3 of them in the store window. How many possible displays can be made if Part A, cupcake flavors can be repeated and the order they are displayed in matters? B is saying cupcake flavors can't be repeated and their display order is important. C is saying we only care about which 3 flavors are in the display, meaning we don't care about the order. So in part A, we could put 3 of the same flavor of cupcake in the window and that doesn't matter. They're telling us it can be repeated, but they're also telling us the order that they're displayed in matters. So this is going to be one where we have to use the product principle. The most important things here is that it can be repeated and that order matters. Now they may not word a problem and always like this and say order matters. They may use some other type of phrasing, so it's important that you pay attention and try to figure out if order matters or doesn't matter in that situation. So we'll use the product principle. So we have 3 spots in the store window and there's 9 flavors, and since we can repeat, we have 9 flavors every time. It's the same thing as 9 cubed, which works out to be 729 different possible window displays. Part B is saying we can't repeat flavors, so once we put a flavor down once, we can't use it again, and we care about the order of the display. So this tells us that we can either use product principle or we can use a permutation. If we use a permutation, we're going to be doing 9 permutation 3, and this gives us 504. We can use the calculator for this. If we were to use the counting principle, we would end up doing 9 choices for the first spot. We have 8 choices for the second spot, and then 7 choices for the third spot, which also multiplies out to 504. Now let's say you have a problem like this on an exam. Unless you're given specific directions, you can choose to solve this either way. Now part C, we only care about which 3 flavors are in the display. So we don't care about the order, we just care about, what flavors are in the window. This is a problem that we would solve using a combination because we don't care about order, but we do care about what's in the group. And they didn't directly say you're not allowed to repeat flavors here, but it's implied that you're not allowed to repeat because they're talking about 3 flavors, meaning like 3 different flavors. So this is going to be 9 choose 3, and that comes out to 84.